Hello, I'm Yağmur Öztürk and I'm going to present you my applied electromagnetics project. In this project, we're required to design a cavity resonator at an arbitrary resonant frequency between 500 MHz and 1.5 GHz. A cavity resonator is a segment of a waveguide with high quality factor, and it is used for oscillation and amplification purposes generally. And cavity resonator is an efficient tool to work with at higher frequencies than 3 MHz. In this project, I'll be using monopole antennas, one to excite the resonator and the other is to observe the output signal. I have chosen the frequency as 750 MHz and the mode is chosen as TE101, which makes M and P 1 and N 0. I have used aluminum foil to cover the box and construct the conducting walls of the cavity resonator. The dimensions of the cavity resonator are determined by trial and error from the resonant frequency formula that can be seen here. And the two lengths are 26 and 31 centimeters. And the third dimension is not really important because n is 0. And the final form of the cavity resonator can be seen here. It was important to make the wall smooth and cover the box completely with aluminum. And the next part was designing the antenna. The length should be larger than lambda over 4 and lambda is calculated as 40 centimeters by C over F. So the antennas were 10 centimeters and they were built with copper wire. To find the optimum location of the antenna, we should consider the points at which the electric field is maximum. And the x and z components of the electric field is 0, so we should consider the y component, and it should be maximized with x equals a over 2 and z equals d over 2, and these locations correspond to the center of the top face. And these were the preliminary work. The setup for the experiment can be seen in the figure. A network analyzer and a signal generator were required. Initially, the first antenna was connected to the cavity resonator, and the impedance of the cavity resonator was measured with Smith chart mode of the network analyzer, and then the return loss was measured with the dB graph. The return loss should be greater than 10 dB. As seen here, the impedance of the cavity resonator is approximately 50 ohm with a small imaginary part. However, it's not necessary to match this cavity resonator because from the previous labs we already know that even after matching, we might still have such a small imaginary part. And it was also seen from the decibel graph that the return loss is greater than 10 dB as required. One important thing that was noticed from both Smith chart and dB graph was that the measured resonant frequency was 730 MHz, which is 20 MHz less than the calculated frequency. The reasons of this will be discussed in the conclusions. You can see the Smith chart again. After these measurements, we know that the cavity resonator works properly. So then I connected the second antenna to the cavity resonator and the signal generator and measured the output. It was around 1.24 volts. And the input was also measured by directly connecting the network analyzer to the signal generator, and it was around 1.77 volts. So there's around 30% loss, which is acceptable. And to conclude, the cavity resonator works properly with the required return loss and acceptable loss at the output. The errors, such as the shift in the resonance frequency, are mostly due to the non-perfect structure of this cavity resonator. The walls were just covered with the conducting material, not made of it. And also it was crucial but hard to keep the antenna stable, so this might have affected the measurements. And this is the end of my presentation. Thank you for listening to me.